Alright guys, so today lecture will focus on shear force and bending moment diagram. So this is continuation of your bending topic, in which you have already seen multiple topics like calculating normal stresses and then shear stresses, and moment of inertia calculations. So today's lecture is basically only for drawing and understanding what do you mean by shear force and bending moment diagram. Alright. So we'll start this. So when we say a beam, so you can have multiple types of beams. So this lecture I'll go by a different way as in I'll follow some different procedure to solve the numericals for your gate rather than doing calculations which are given in strength of material books. So the formulation is something like this. What do you mean by shear force and what do you mean by bending moment? Diagrams we'll see. So let's say you have a cantilever beam, and on this cantilever beam you're applying a point load here. Similarly, let's say you have a simply supported beam and you're applying a UDL, which is uniformly distributed load over the entire beam. Now shear force and bending moment diagram says when you move along the length of the beam, let's say length of the beam is L in both the cases, how forces are being experienced by that cross section. Now what do you mean by this? You have this beam, you are applying a load here. What load is experienced by this cross section? When you move forward and you remove this, still you have the same cross section, right? What load is being passed when this load is applied here? What is load at this section? Similarly, what is load at this point? What is load at this point? All these are loads acting parallel to cross section. So we are naming it as shear forces. This shear force will lead to stresses. It can be it is usually shear stresses, which we have seen in previous lecture, and you are using the formula SAY divided by IB. This S becomes shear force acting at that cross section. Now what do you mean by this? You have a different shear force. Let's say this is load P acting at this cross section. There is a possibility that different load will act here. In this case it will remain same. Different load, different load, different load. So wherever you want to calculate stresses, let's say you want to calculate stresses at midpoint, so you need to calculate shear force there and then use your basic formulas. Similarly, same expression goes for bending moment. So I hope you can visualize this. Moment here is 0 because it is free end, and force, there is no perpendicular distance. As you move forward, this is P into some distance. If you go to the center point, it is P into L by 2. If you go here, it is P into L. So when you move along the length of the beam, your movement as well as your forces are continuously changing. How these are changing, you want to plot them, and that is what known as shear force and bending moment diagrams. There are multiple questions asked in your exams. There is one question in 2019 GATE Aerospace. So we'll be doing all those numericals. I'll be going by a different method which is more of a property based. So rather than doing calculations, you can see the beam and you can see your options and cut down the wrong options by checking for the properties they should possess. I hope it is clear to everyone what do you mean by shear force, what do you mean by bending moment. So shear force is nothing but whatever force is acting at that particular section. Section means part of the beam. It can be anything. Similarly, bending moment diagram is at every section what is the movement experienced when you apply load here or when you apply load like this or different combinations. So I'll give you different numericals and then we'll try to solve these numericals. So what we'll do is I try to solve all these numericals, all these theory with a numerical kind of thing, and then we'll try to formulate some what we can say properties out of it. So I'll start with first numerical. Alright, so I'll give you a simply supported beam. Let's say you have a simply supported beam. Alright, and load is applied at center point P. At center point, a load applied is P. This point is A, this point is B, and we don't know the reactions. So we have already seen this in previous lecture, how to calculate reactions when you have any kind of beam, whether let it be cantilever or simply supported or overhang beams. So you can refer the previous lecture for calculations. Because it is symmetric for time being, so I can happily say this is P by 2 and reaction at A is P by 2. Guys, again I am repeating, if you have any doubt in any of the formulation in any of the lecture, you can individually contact me, or you can post your doubt in the portal itself, or you can go to the doubt clearing group and post your doubt. We'll try to clear everything when we have any of these doubts. So I'm assuming that you have already seen the lecture and you know how to calculate the reactions. once you have this, now I'll try to draw shear force and bending moment diagram with some rules which I want you to understand through a numerical. So I don't want to do calculations. I want to simply draw this shear force and bending moment diagram. Alright, now we'll first understand how to draw shear force diagram for any beam. Just keep one thing in mind. The rule which we'll follow, or the sign convention which we'll follow, will be RUN, run. Now what do you mean by this? Right hand side, any upward force will be treated as negative. So right upward negative. Now keep one thing in mind. If you want to change this convention, you can change any two things. Now what do you mean by this? You're still on the right hand side. Alright. Upward, I'll say downward. So one thing is changed. You cannot change one thing. You have to change two things. Not one, not three. So right same, upward becomes downward, then negative should become what? Positive. They both are one and the same thing. So if your upward force is negative, your downward force should be positive. Similarly, you can take this to the left hand side. Now, keep this in mind, only two things can be changed. So right becomes left, one thing is changed. Upward, I am saying upward. Now negative has to change to what? Positive. Another way of looking into this, left remains left, upward becomes downward, positive becomes negative. So this is the sign convention. You need not to learn anything, just keep this in mind and change any two quantities. Keep it on right hand side, upward, downward, down, not negative, positive. Come to left hand side, when you come, right becomes left. So you can only change either one. So upward, positive, upward as it is, negative becomes positive, and right becomes left, downward remains downwards, positive becomes negative. So only change two things at a time. You cannot change one, you cannot change three, and you have your same sign convention all the time. So I'll be not using any of this other formulation because it's difficult to remember all this. I'll keep run in mind, right, upward, negative. Alright, now this is the way we're going to draw it. I'll start from right hand side. This is what my rule is, not my rule, my way of solving a numerical. You can always start with left hand side, that's totally up to you. But you have seen your deflection of beams lecture in virtual work. I always try to move from right hand side. So the thing is this, when you're standing at a point, always see what is happening on the right hand side. You should never see what is happening on the left hand side. Left hand side has no significance on your system when you are moving from right hand side. For example, I'll stand at point B. I'm standing at point B. So don't see anything on left hand side, see what you have on the right hand side. I don't have anything. So what should be your shear force? It should be 0. Whatever you have on the right hand side, you need to plot that. Alright. Now, guys, this is kind of important part. Now, we were at point B. Now I'm coming to very small distance on left hand side of B. Very small distance. Let's say 0.000001 mm. Now you are slightly on the left hand side. See what force you have on the right hand side. Force. So force we have on the right hand side is what? P by 2 now. Correct, right? So P by 2, sorry, P by 2 is the force on the right hand side. Again I'm repeating, don't see anything on the left hand side. P by 2 is the force on the right hand side. Now this is upward force, right, upward. So I should mark this force as negative in my diagram. So what should I do? I am at point, I'm on slightly on the left hand side. What should I do? We should have a sudden jump with a magnitude of P by 2. So I have reached here. I hope it is clear to everyone. Now what we need to do is move slightly on the left hand side. What force you have? Still P by 2. Move here. Still P by 2. Move here. Still P by 2. Now you have reached C. C, don't look for this force. See what you have on the right hand side. Still we have P by 2, right? That means when you move from this point till point C, the force is constant and it is nothing but what? P by 2. I hope it is clear. Now you move further on the left hand side. When you move further on the left hand side, you observe there is a force P acting downwards. Right upward is negative, so right downward will be positive. So there is a force P acting downwards. P is positive. P by 2 is acting upward. So what is the net force acting here? Plus P minus P by 2. So it is plus P by 2. Correct, right? Now the issue is What should I do? So I'll tell you the easiest way. Whenever you have doubt, start always from right hand side. Wherever you have a load or anything which is creating issue in your mind, stop at that point. Don't go further after that. Alright? Stop at that particular point. Start from left hand side. Right? Now, I'll repeat the same procedure from left hand side. I am standing at point A. Now see only on the left hand thing. Don't see anything on the right hand side. We don't have anything on left hand side. So my force is 0. Alright? Now go slightly on the right hand side. If you come here, now you observe suddenly there is a force P by 2 going up. Now what is the sign convention? Left, upward, negative becomes positive. So anything on the left hand side going up is positive for us. What is the magnitude of that? P by 2. So there is a sudden jump and you have reached up in the P by 2 magnitude. Now if you move like this, still on the left hand side you have P by 2, still P by 2, still P by 2, and when you reach here, still on the left hand side you have what? P by 2. So you cannot change your shear force in any of these things. Correct, right? So this is the easiest way, guys. Start from right hand side, reach wherever you have confusion, stop. Start from left hand side, reach wherever you have confusion. When you reach two confusion points, just simply join them. Now this diagram is negative and this diagram is positive, and we have our shear force diagram ready for this simply supported beam with a point load exactly at the center. So I will be doing this in multiple numericals, then we'll see some of your exam numericals. Maybe it will be clear. By the end of the lecture, you should be able to draw and plot any kind of shear force and bending moment diagram for any kind of beam. Alright, now we'll go for bending moment diagram. Now bending moment diagram is something like this. We know our sign convention, we have already following this in our deflection of beams. So any movement will be considered positive if it is following. Means when you come from right hand side, any movement like this is positive. When you come from left hand side, any movement like this is positive. Keep this in mind. Alright, let's draw the bending moment diagram. So you're at point B. What is movement here? 0. Now keep this in mind. When you're coming from right hand side, only on the right hand side forces you should see. Don't see that when you're standing at point B, this will create some movement, this will create some movement. No. Because I'm coming from right hand side, only right hand forces can create a movement in the beam. So when I'm standing at point B, there was no one on the right hand side, so there is no movement. Now think about this. When you move towards left hand side, any distance, what you observe? P by 2 into some distance. So P by 2 into some distance is creating a movement. Now what happens if we move forward? P by 2 into some distance. Now this distance is continuously increasing. Correct, right? So usually, if you see our deflection numericals, we'll write this equation as P by 2 into X, where X varies from 0 to L by 2. That's what we usually do, right? So what I'm trying to say is, bending moment diagram for a point load is linear. That means you're multiplying it with some distance. Correct, right? So 0, increasing, 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 and you will reach C. After that I have doubt, I'll stop. How this load is increasing? It is increasing linearly. So I'll start from 0, and is this positive or negative? This is positive bending moment, right? Wherever you go. So this is positive bending moment. So I'll just increase this and I'll reach point C. I have doubt, I'll stop here. Alright, now what I'll do is, I'll leave right hand side of the beam, I'll come to left hand side of the beam. Now same thing, what is movement here? Now see what loads you have on the left hand side, no loads, right? So I'll start with 0. If you move forward, your movement is continuously increasing, and this is the movement it is creating, force into perpendicular distance at any point you can observe. And what is this movement? Positive for us when you move from left hand side, start and you reach here. So by straight lines, point loads. Any point load will create linear variations. P into X, P by 2 into X. All the X variations, X to the power 1 are nothing but linear variations. So you end up with this kind of diagram. Can anyone tell me what is the magnitude here? You either come from right or from left. Magnitude remains same. Can you tell me when you come from right hand side, what is the movement? P by 2 into L by 2. Correct, right? When you come from left hand side, P by 2 into L by 2. So what magnitude you observe here? PL by 4, and this whole diagram is positive with our sign convention. Sometimes people say this as sagging smiley face, but I have given a different formulation for bending moment sign convention, which is basically we are following Maxon or let's basic statements. For time being, don't enter into that. Just keep this in mind. So this is an overview of how shear force and bending moment diagrams are drawn without doing any calculations, and you can happily just draw the diagram. Any one of the options will be present in your exam and you can mark the properties. Alright, now maybe in this diagram I'll try to give you a few properties. Maybe it will help you in the future numericals. Try to observe few things. I'll give you the equations once we are done with this, but first you should know how to draw this, then we'll get property out of it. So the properties are this. When your shear force diagram was constant shear force, see, it's a straight line, right? What do you mean by this? Shear force here is P by 2, P by 2, P by 2, P by 2, P by 2 with a negative sign. Shear force here is P by 2, P by 2, P by 2, P by 2, P by 2 with a positive sign. It remains constant. And then there is a sudden change at a point load. So wherever you have a point load acting in your beam, guys, this is first property. I'll be summarizing all the properties in the end, but this is the first property. Whenever you have a point load acting in the beam, your shear force diagram will see a sudden change, dip in your diagram. See, a point load P, a sudden change, dip of magnitude P itself. This is plus P by 2, this is minus P by 2. This is what you observe. First property. Second property. Wherever you observe your shear force diagram is constant, your bending moment is linear. Now what do you mean by this? Your bending moment diagram is one order higher than shear force diagram. Now what do you mean by higher order? Anything constant, anything constant in maths is, let's say C. What do you mean by higher order? C into X. What do you mean higher order? C into X square, C into X cube. So if your shear force diagram is constant, your bending moment diagram is linear. If your shear force diagram will be linear, your bending moment diagram will be parabolic or quadratic, and so on. Other words, your shear force diagram is one order less than your bending moment diagram. Now we will see this in equations. What do you mean by higher order and one order less? When you integrate things, right, when you have X, integrating it will become X square by 2, so you are increasing the order. When you have X square and you differentiate it becomes 2X, you are decreasing the order. Keep this in mind. With this we will be developing relations between shear force and bending moment. Alright, so it is present in your, if you have the material, guys, all these points I have already written. If not, please go back in the same video and see how we have done, how what rule I have followed, and what are the properties I am taking out of the diagram. We will solve many numericals on this. There will be a separate lecture of shear force bending moment diagrams, exam numericals, and some additional numerical itself. For time being, try to understand how we are going to attack this if this comes in your exam. Alright, so I'll keep this handy and I'll give you one more beam. Let's say you have a cantilever beam, alright, of length L, and in this cantilever beam I am applying a load P. What is the corresponding shear force and bending moment diagram? I don't want to solve numerical, I just quickly want to predict the behavior. Alright, so I'll do one same thing. I'll draw this line. This is my shear force datum, this is my bending moment diagram datum. Alright, keep basic thing, and we know this for cantilever beam it's not advisable or not required to calculate reactions because we can always move from free end, it saves your time. But in simply supported beam, first thing you should always do, whatever your numerical is, you need to calculate the reactions first. Then only you can solve your numerical. Right? So I'll follow the same method. Run for shear force. Alright, tell me guys. So we are standing at this point. So when you're standing at this point, on the right hand side we don't have any shear force. So I'm still at this point. Correct? Now go to a very, very small distance on the left hand side. When you go to the very small distance on the left hand side, you observe there is a force P which is acting downwards. So your force is acting on the right hand side. It is not upward, it is downward. If your right is same, it becomes downward, then it should be what? Positive. So how much magnitude? I should directly go to a magnitude of P upward at this point. Alright, now you are at this, come here, what force you have on the right hand side? Still P, still P, still P, still P, and you have reached here, force on the right hand side is still P. Now what do you mean by this? Throughout the length of the beam, your shear force is constant with a magnitude of P and it is positive. Easy, straightforward. Now I'll come to bending moment diagram. Alright, I'll start from this point. Again, the sign convention is this for our bending moment diagram. Can you tell me what is movement here? Force there is no distance, so movement here is 0. Now what you'll do is, you'll come here. Once you come here, P into some distance. So P into X. Come here, P into X. Come here, P into X. So what is happening? Movement is continuously increasing as you're moving along the length of the beam. Correct, right? And it is linear. Now the question is it positive or negative? Because I'm tracking right hand side and it is coming in this direction. So it is positive or negative? It is negative, right? And linear, negative. So I'll start with 0. I'll go with a straight line that is linear and I'll reach my fixed end. And I've reached my fixed end. And what is the magnitude? Here if I'll say P into L. And we'll say it is negative. Now let's check out the properties. Wherever you will see a point load, your bending moment diagram, your shear force diagram is having a dip, going up or down. Correct, right? I hope this part is clear. Second property, your shear force is constant over the whole length, then your whole bending moment diagram should be linear. You cannot violate these properties. If your shear force diagram is constant, this should be linear. So we have satisfied both the properties, we end up with this solution. I hope it is clear to everyone. Now what we'll do is, I'll give you more numericals. We'll try to draw a shear force bending moment diagram for all these numericals, and maybe in last 10-15 minutes we'll try to solve what numerical they have asked in your previous years. Alright? I hope this is clear. So so this is first numerical, this is second numerical. So we have solved one simply supported beam, one cantilever beam with point loads. I'll go with combination of point load and UDL and maybe try to create few confusions so that like all our doubts are clear. Alright. Alright, guys. So third numerical which we'll solve is, we have a simply supported beam, alright, and let's say in mid section of length L by 2, I'll put a UDL. Alright, so we have this point A, this point B. In the length L by 2, you have this UDL. This is L by 4, this is L by 4. So whole length of the beam is L, and you have a UDL in some small portion of it. You can definitely draw it for, alright, we'll do one thing, we'll make this as next numerical. So third numerical, what we'll do is, in this simply support beam, I'll make UDL everywhere. So that you know what happens with UDL, then we'll try to complicate things in the end. Now, what should be first thing is, so load is small w Newton per meter. Means it is a distributed load. If you multiply this with length, Newton multiplied by length, meter got cancelled out and you have force then. I hope you know what do you mean by UDL. Alright, now again I don't want to do calculations, but still length of the beam is L. Can you tell me what are the reactions? What is the total load acting on the beam? This W is acting over the whole length, right? So W into L will be the load acting. W into L is the load acting, then reaction at B will become WL by 2 and reaction at A will be WL by 2. Guys, anytime you have this doubt, please refer to the previous lecture in which we have seen how to calculate reactions for any sort of beam. Alright, now I'll draw shear force and maybe you people can help me in this. So what should be moment at point B? 0, and this is the boundary condition for hinge support and roller support. It cannot support movements unless and until it is overhang beam. Alright, we'll come to overhang beams separately. So you have at point B, you're trying to draw shear force. So just see what you have on the right hand side when you're standing at point B. On the right hand side, I don't have any loads. So I'm at point 0 only. Now come slightly on the left hand side, you observe there is a sudden load WL by 2, which is kind of a point load. And we know at point load, our diagram should either go up and down. It should do something at that particular point. And your units or your sign convention is run. So right hand side, upward force is considered to be negative and your magnitude is what? WL by 2. So I'll start from here and I'll directly come down with the magnitude, and this magnitude will be WL by 2. I hope it is clear. Now what we'll do is, I'll move further away. But now you observe, don't see anything on the left hand side. Now you observe, there is a point load which is going up with a magnitude of WL by 2, but also there is a UDL which is coming down. Correct, right? Now I want you to track UDL values. I only need forces. This UDL is force per unit length. So you need to multiply it with length to convert that into force. Now WL by 2 is itself a force. Now force is going up, some UDL force is coming down. Correct, right? And now how to track UDL? Think about this, guys. How much UDL is acting on the right hand side? Whatever length you have. Let's say X. You move further away, more UDL is acting over the whole length. So X is increasing, so your force is increasing, because now force is W into X. Still more force on the right hand side, still more force on the right hand side. And how this force is increasing? Because you have a UDL, to convert that into force you need to multiply it with length, and we are taking that length parameter as X. Now what do you mean by this? X equals to 0, something, 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 L by 2, something, 3L by 4 and L. So X is between 0 to L, and X is continuously increasing when I am moving from this point to this point. What do you mean by X? It's linear variation. Now think about this. You start from this point, correct? And you need to, now tell me, you should come down like this or you should go up. You should go up. Why? This point force is going up and it is negative. This UDL is going down, which is right downward positive. So one is positive, another one is negative, so they are cancelling out the effect. So it is something like this. I know this diagram, guys, so I am just directly drawing this. But if you have doubt, I'll tell you what we can do. You come, start from this point, reach here, stop. You have doubt, come to left hand side. Now what you observe on left hand side? At point A, there was nothing. When you move slightly on the right hand side, now see on left hand side what forces you have, WL by 2, and it is going up. Going up means positive with a magnitude of WL by 2. So you end up with this diagram basically. If you have doubt, you are here and you are here. This is clear to everyone. Now once you have, you need to join these things. Now because it is UDL, right? UDL means linear variations in shear force diagram. So you just need to draw this with a linear line. This becomes shear force diagram for a simply supported beam with a UDL load. If I want to draw a bending moment diagram for this, this is easy and straightforward now. What is this? At point B, 0, because no force on the right hand side, and this force will not create any movement because there is no distance. Similarly, no force here. Correct, right? Now with the property itself, I know all these things the diagram should look like, but if not, you can tell me this. If you want to calculate movement here, what should be your movement terms? Your movement terms will be WL by 2 into X, correct, right? Minus small w into X by 2. We have done these equations a lot when we have used virtual work method to calculate deflections. Anytime you have doubt in writing these equations, please go back, listen to that lecture. You should be very clear and confident in writing the movement equations. So if I'm just writing for your reference, let's say I want to calculate movement here. So movement for this section will be WL by 2 into X, this one. So this is X. This is positive, right? Now minus this UDL is forcing it down. Now what do you mean by UDL is forcing it down? W into X is the force, into X by 2 is the movement it will going to create, and this equation is valid from this point till this point. Now what my point is, when your shear force, if you want to write shear force expression, guys, shear force means only forces. So what are forces you have on right hand side here? It is WL by 2 going up. Going up means right upward negative, so I'll apply a negative sign, and plus UDL is coming down, and what is the force acting? W into X. Now what I'm trying to say is, when you have a UDL, your shear force is a function of X. X means linear variations, and your bending moment is a function of X square, means parabolic variations. So from this point to this point, if you want to draw your bending moment diagram, should be a parabolic kind of behavior, and it will be something like this. Alright, now I'll tell you few properties how I knew this is the correct answer. When this was linear, this should be parabolic. First property satisfied. Correct, right? Second property, wherever you have a point load, there only your graph can go sudden up and dip. Otherwise, it should be smooth or constant. You cannot have dip up and down when you have when you don't have a point load. Second property. Now, third property I am introducing, the point at which your shear force changes its sign. It goes from negative to positive or positive to negative. At that point, your bending moment should be maximum. So I knew actually at this point, your bending moment will be maximum. It doesn't look proper, but it is kind of this. Now, if you want, you can check this magnitude. How to calculate? You have written moment equation here, right? Center point means x is L by 2. Check. At x equals to L by 2, what is your movement, guys? Tell me. W into L square by 4 minus L by 2. So L by 2 into L by 2 is L square by 8. So what this magnitude becomes? This becomes WL square by 8. This is the maximum bending moment acting at the center of the beam. So I'll tell you how this is useful. If someone says you have a simply supported beam with UDL, what is the maximum normal stresses acting on the system? Now, maximum normal stresses is nothing but this formula, if you recall. M into Y by I. So if you want to maximize this, you should maximize this also. So what do you need? In this whole length of the beam, where is your movement is maximum? Correct, right? Now, this bending moment diagram will come and help you. If you want to calculate your maximum stresses, please go to the center of the beam and then use your formulation of this, calculating inertias and Y, and then use your movement as WL square by 8. Then only you're calculating maximum normal stresses. If you calculate here, right, with the same formulation, you feel you're calculating maximum normal stresses, but not, because your movement is not maximum here. This beam is never experiencing any movement, maximum movement, apart from center of the beam. I hope this is clear. So we have seen three properties now. Wherever your shear force changes sign, the bending moment diagram becomes maximum at that point. I hope it is slightly maybe clear. I'll tell you one very easy and simple shortcut. Maybe we'll discuss this in coming lectures. Whenever you draw any bending moment diagram on the upper side, try to have these bulging parabola. Whenever you draw anything on the lower side, there is a reason. It's not a learning method. There is a reason. We'll talk about this. Try to have some cave parabolas, something like this. You will observe in the next numerical. I hope it is somewhat easier, somewhat clear how to draw shear force and bending moment diagram. Now we'll go to fourth beam and try to apply these concepts. There are infinite numericals because you can have infinite combinations of beams. Just keep few properties in mind. Overall rough idea is more than enough to draw a beam. You don't need specific calculations. So I'll go to fourth numerical. I'll create a cantilever beam and apply a UDL. So we have all cases in our mind, and UDL is again small w, Newton per meter, and length is L. I want you to draw shear force and bending moment diagram for it. Pause the video, give it a try, and then we'll see what solution you're going to get. We can verify. Alright, so let's do this. So you are at this point. Tell me guys, what forces you have on the right hand side? No force. So 0. Correct, right? Now, is there any point load acting here? No, right? So your shear force diagram will not going to see any sudden changes. It will be smooth kind of thing. So if I'll come towards this point, you have some force acting on the right hand side. Can you tell me what is that force? W into that distance. That is W into X. When you come here, it is W into X. When you come here, it is W into X. X is continuously changing. When you come here, W into X. Now what do you mean by this? When you move from this point and you're starting from 0 and you're moving forward your X is continuously increasing. Correct, right? Your X is increasing means you have a linear variation. So we know from this point till this point, I have a linear line to draw. Now next is, should I draw positive or negative? Again, same thing will come. Right upward is negative. When I'm moving from right hand side, all these forces are acting downwards. If upward is negative, downward should be positive. So my shear force diagram will start from this point and we'll go to this. It will be something like this. Why it is linear? Linear shear force when you have UDL. Constant shear force when you have point load. We'll see what happens in movement terms. Alright, I hope it is clear. So it is positive. Can someone tell me what is the magnitude? Force on the right hand side when you're standing here, and see what you have on the right hand side. We have W into L. So this becomes your shear force diagram. Bending moment diagram. Now tell me guys about bending moment diagram. You are at free end, no one is helping you, no one is stopping you to rotate. So movement is 0 here, force into distance. Now can you tell me once you are here, once you reach here, what movement you expect? On the right hand side only see. So what is load acting? W into this distance which is x, this is load, multiplied by half distance which is x by 2. So no need to do these calculations, write these equations again and again. We already know actually when you have a linear variation here, it should be a parabolic behavior here, correct, right? And the only thing I need to understand is whether it is positive or negative. We know when we stand at any point, the movements will be these movements, positive or negative, negative. So I should draw a parabola kind of thing from this point to this point. No need to worry in between because it is continuous UDL, nothing is happening in between. And you just want to draw it. Now this was the point I was making before. When you draw any parabola on positive side, try to draw bulgy parabola. When you draw your parabola inside, try to draw this kind of a parabola. It's not a rule to learn, but again, can you tell me what is the movement here? So whole load acting on the right hand side will be W into L. This is load multiplied by distance. So how UDL works? W into L is the total load acting. Assume in your mind that it is acting at the center. So movement it is creating is multiplied by L by 2. So your bending moment diagram is this with a negative sign. I hope it is clear. I'll tell you why this bulging comes with the properties. When your shear force is continuously decreasing, your slope of this diagram should be decreasing. It should have maximum slope here, minimum slope here. Don't enter into this confusion for time being. Just keep it as a note. Anything above, it should be these kind of parabola, which I've seen in the previous numerical. Anything below, it should be these kind of parabola, like concave, and this is kind of convex. You have a bigger parabola present. Alright, so we'll go to fifth numerical. Alright, so now what we'll do is I'll have a cantilever beam, alright, and I apply a moment M here. Maybe another case. So for this again we need to draw shear force and bending moment diagram, and this is beam length L. This is your shear force, this is your bending moment diagram. Alright, now we'll go slow. I'll stand here. What forces you have on the right hand side? No force. You come here. What forces you have on the right hand side? Movement is not a force. I need only forces in shear force diagram. So no force. When you move on here, right hand side, no force, no force, no force. So what should be a shear force diagram? Nothing. It should be a straight line at 0 only. There is no shear force in this. Correct, right? Now I'll come to bending moment diagram. What is movement acting here? There is a movement rolling up, and we know this is positive when we stand here. So we'll directly see what? We'll go up with a magnitude of M. Alright, now you come here, positive, same movement M. When you come here, same movement M. When you come here, same movement M. When you come here, same movement M. What do you mean by this? This movement remains constant over the entire length with a magnitude of M. And guys, we should know this. This is the property. Now when anything is, I told you right, higher order. What is shear force? 0, right? What is higher order of 0? Constant. Other way of seeing it. If this is constant, what is derivative of this? Constant derivative is 0, right? Now, keeping this in mind, I want to give you a few properties. Try to understand these properties. So first property is, alright, and then we'll try to spend more numericals. There will be definitely one more lecture on shear force bending moment diagram for solving more numericals. I hope this lecture will give you an overview and you can try out more numericals. But what are the properties we have? The properties is something like this. When you have a movement, I hope you know the movement terms. Alright, okay. Let's give you an overview of the entire problems. Y, we'll say, is deflection of beam. So when someone says calculate deflection of beam, you'll say y is equals to WL cube by 3 EI and y is equals to WL cube by 48 EI. Some calculations you'll do. When you differentiate this y, that means dy by dx, you call it as slope. So slope of the beam at some point. Slope of the beam in cantilever beam at fixed end is 0. Similarly, slope in a simply supported beam at the midpoint is 0 when you apply a unit load, and so properties we'll see. Now what you'll do is, guys, keep in mind I'm continuously differentiating it. You differentiate it further, d square y by dx square. Now this doesn't represent movement absolute value, but I hope many of you have seen this. EI, which is flexural rigidity, into this is nothing but your momentum. Now don't worry about this negative sign, that totally depends upon what coordinate system you have chosen. It can be plus also, depending upon whether your x and whether you have taken your y-axis upward positive or downward positive. So don't worry about this. The only thing I want you to understand is deflection. You differentiate, you'll get slope. You again differentiate, you'll get some movement terms. So movement is second derivative. Now what you'll do is you'll differentiate this movement again. Whatever you're going to get is known as shear force. When you differentiate your movement, you're going to get shear force. An absolute value, if you'll see here, will be minus EI d cube y by dx cube. So this is nothing but represents your shear force. Alright, and the last point is, if I differentiate my shear force again, I am going to get, which is known as uniformly distributed load with a negative sign. So it becomes what? It becomes fourth order equation. Sometimes this can be referred to as shear flow also. So no need to worry about any of these things. What you need to understand is this: deflection, differentiate, slope, differentiate, movement, differentiate, shear force, differentiate, shear uniformly distributed load. Alright, now I want you to understand these properties, why we are needing this and how we are using these properties to solve our numericals. I'll go to our main formulation. So our main formulation is this: you have some movement, you differentiate it, you end up with this formula. So I'll write this: dm by dx is equals to v. That's what you are saying, correct, right? Now think about this, guys. Whole essence is this equation. Now what do you mean by this? If your movement, let's say, is 10, what do you mean by 10? A constant number. If your movement is constant, when you differentiate any constant quantity, what you expect? V should be equals to 0. That means your shear force should be 0. Now check if question number 4, in which you only have movement, your shear force was 0 and your movement was constant. That's what we were saying. When you have any shear force diagram, your movement is higher order. Now what do you mean by higher order? If your movement is linear, let's say function of x, when you differentiate function of x with respect to x, you're going to get a constant quantity. Check your diagram 1. When you have your movement as square terms, x square, parabolic behavior, when you differentiate that, you are going to get linear terms. Check your simply supported beam with UDL or cantilever beam with UDL. So what I am trying to say is shear force and bending moment diagrams are one order difference. Bending moment diagram is always one order higher. Now why one order higher? If you integrate this, how to get movement? You need to integrate your shear force and you'll end up with movement. Now what do you mean by this? If this is function of x, movement will be x square. If this is constant, this will be x. I hope it is clear. Similarly, both equations are one and the same thing. Both equations are one and the same thing. So no need to get catch involved in this. I have already used these properties in solving the numericals. This is only for your understanding and summing up like how shear force and bending moment diagrams are linked together. So if numericals can be framed in your exams as if this is the beam, tell me what is shear force diagram. This is the beam, tell me what is a bending moment diagram. There can be a numerical saying, this is the shear force diagram, what is the corresponding bending moment diagram out of it. This is the bending moment diagram, what is the corresponding beam out of it. Any way they can give you the data and ask you to calculate the other quantity. So it's totally up to you. You should go with the properties. Alright, in the end we'll try to summarize all the properties. But I hope this point is clear to everyone that movement is always one order higher than your shear force. Correct? Now second property is, think about this. In maths, if you want to maximize anything, what you'll do? You will differentiate that quantity and equate it to 0. What do you mean by this? If I differentiate movement and with respect to x and equate it to 0, what I am going to get? Maximum movement. Correct, right? And for doing that maximum movement, what you are doing? You are substituting your shear force as 0, right? And this property I have already discussed. Wherever your shear force changes its sign, it becomes 0. positive to negative or negative to positive, at that particular point your bending moment diagram is maximum. This is the property I already told you before. So if you understand this equation, right, everything is present. Now there are other catchy terms, difficult terms you will see in your materials or in any strength of material book. What they usually say: area under your shear force diagram. Area means integration. Area under shear force diagram will give you the bending moment. Same thing. What they are saying: slope of movement diagram, slope of bending moment diagram. Slope means derivative. Will give you what? Shear force. So there is only one equation, and they are writing that equation in 10 different ways and creating 10 properties. But what is the simple equation? dm by dx is equals to v. I hope I have made my point, what I am trying to say. So don't worry about any of these things, guys. Keep this in mind, how your bending moment diagram and your shear forces are connected. Just keep one statement in mind: your bending moment diagram should always be one order higher than your shear force diagram. Now, one order higher means if anything quantity is 0, higher order is constant. If anything is constant, higher order is linear. If anything is linear, higher order is parabolic. If anything is parabolic, higher order is cubic, and so on. Alright. Area under your shear force diagram will give you bending moment diagram. If you slope of bending moment diagram will give you shear force diagram. Wherever your bending moment diagram goes to maximum, your shear force should change its sign and it should go to 0. All these properties you have in mind. I hope it is clear. Now I am coming to the last note of theory, then we'll again come back to numericals. Note is something like this: if your shear force is 0 anywhere, correct, right? What do you mean by shear force is 0? That means dm by dx is equals to 0. Correct? Now what do you mean by dm by dx is equals to 0? M, we know it's one order higher, is constant. Now what do you mean by m constant? Throughout the beam, your m is constant. This is referred to as pure bending. We are seeing this for the first time. We have seen symmetric and unsymmetric bending, but this is what referred to as pure bending. So what is the definition of pure bending? When throughout the length of the beam, shear force acting is 0, then the beam is under pure bending. What do you mean by pure bending? There will be no distortion of the cross section and the plane section will remain plane. This is what known as pure bending formulation. So there is no shear force. No shear force means your cross section will not change. Your cross section, see, these are shear forces, right? You have a beam, this is a shear force. What shear force tried to do? It tried to change the shape of your cross section. So if your shear forces are 0, what only thing can happen? This beam can only bend. You cannot change your cross section properties. So pure bending is when there is no distortion, no warping of cross section, and there is only rotation or transverse movement of fibers you are constraining, you can say taking into account. You are neglecting all the shear strains in the beam. This is referred to as Euler-Bernoulli beam. Alright. So I hope these properties are somewhat clear. Let me come to one more numerical. Just for the competition, can you tell me what is an example of pure bending? I hope it is clear to everyone. This was pure bending. Why? Because if you see shear force, there is no force acting, there is only a movement, right? Shear force is 0. That means your bending moment diagram is somewhat like this. So you have drawn your shear force as 0 and you have drawn your bending moment diagram as a constant bending moment. So this becomes what? Pure bending. So you have already seen this case. You have already seen all these properties, but let's try to complicate this and try to solve few numericals. So I'm not giving you very basics now. Let's try to solve it with some good numericals or some combination numericals. Alright, now let's say you have a simply supported beam. I don't know the number now, how many numericals we have solved. You have a simply supported beam and this is L by 4 and L by 4, and in between these two, in length L by 2, we are applying load W Newton per meter. Now tell me guys, what you expect? Shear force and bending moment diagram. What first thing we should do? calculate the reactions, because simply supported beam always needs what? Reactions. So we'll draw a reaction here. Tell me what should be the reaction. So what is the total load acting on the beam? W is acting over the length L by 2. So total load acting on the beam is small w into L by 2. So half of it will be taken by this, half of it will be taken by this. So it becomes WL by 4 and it becomes WL by 4. Now we'll go for shortcut and we'll draw bending moment diagram. Keep properties in mind and then move forward. Tell me what is shear force here. We'll start with 0. There is a point load here, right? So I should have a jump with my sign convention. Right upward is negative. This is on the right hand side, going up negative. So I should come down with a magnitude of WL by 4. Alright, now I'll move here, still same force. I'll move here, still same force. I'll move till this point, still same force. So what do you expect? Till this point, it should remain constant. It should not do anything. Now I have a problem, I have an issue, a different load is coming, I'll stop. I'll come from left hand side. Again, I'll do the same process. I'm at 0. There is a point load going up. Left upward I know is positive. So left upward is positive. So I mark this as positive. Still same WL by 4, sim stale WL by 4, sim stale WL by 4. So I'll keep this as constant. So we know this. Wherever you have point load, this remains constant. Correct, right? Can you tell me what we expect in UDL? In UDL, we expect load to be linear. That means function of x. It should not remain constant. You have started from right hand side, you have reached here. You started from left hand side, you have reached here. In between, I know I should join these points. And definitely it should be linear. Because it is UDL, so it should be linear graphs. I hope it is clear. Now your bending moment diagram is automatically ready. Why? This is 0. This is 0. Go very slow and think in this. I have few properties in mind. What is those properties? When you're this is this bending moment, this is this bending moment. Seeing this only I can draw. I need not to see my beam also. If this is constant, this should be linear in this zone. So I'll draw a linear line. This is constant, I draw a linear line. I hope it is clear. Now this is linear, right? So in this zone, in between, this diagram should be parabolic. So one property is managed. Second, wherever your shear force is changing its sign, there I should have maximum bending moment. So I should draw a parabola in such a way that it should be maximum at this particular point. Why these are linear? Because these are constant. Why there is a parabola here? Because in this zone your shear force diagram is linear. So I'll draw a parabola like this, which is maximum at this particular point. I'm not interested in magnitude numbers. We can anytime write equations and calculate this. If someone asks you to tell me what is this magnitude, you can simply write a moment equation in terms of x and calculate moment here at x equals to L by 2. That's totally up to you how you want to formulate it. I hope it is clear. Check the properties, guys. Load was point load was present in this case, so constant, linear. UDL was present, so linear, parabola. It is changed, goes to 0, bending moment goes to maximum, and this is how your shear force and bending moment diagram looks like for. So this is negative, this is positive, and this is positive. I hope somewhat clear. Alright, so I'll introduce one more numerical. Let's say this is numerical asked in 2019. So all these numericals are solved in your GATE material. I hope you have already seen these material books. You already have these books. So I'm giving you a 2019 numerical. It was asked in your exam for 2 marks. I'll give you one. I'll give you the question and I'll give you 4 options. Then we'll see which one of them, or I won't give you the option also. Alright, we'll see how we do this. Alright, so I'll read the numerical. You can refer to the question papers or refer to the material book. For a 1 meter long simply supported beam, alright, with a concentrated vertical load of 200 Newton and a bending moment of 100 Newton meter at the center as shown in the figure, the current bending moment diagram is. So don't worry about these statements. In simple words, they have given you this. So you have a simply supported beam. You have a simply supported beam. This point is given as P. This point is given as R. Alright. and this is 0.5 meters, this is 0.5 meter. This is the diagram given in the numerical itself. Alright, and at the center point we are applying our 200 Newton load and a movement of 100 Newton meter is applied to the beam. I hope you understand this point. This is point Q. This is a question given, and they have given 4 options. Out of these 4 options, which one of them correctly represents the bending moment diagram? Alright, so it's better I won't give you because then you will, like, it's easy because we are in a practice mode, so it's better you try to draw it yourself. So tell me guys, what should be your step 1? Reactions. Correct, right? Now we have already seen how to calculate reactions in these type of beams. I am telling you the shortcut. So forget about this 100 Newton meter load movement. You have 200, right? So what reaction you expect here? 100. And what reaction you expect here? 100. Both going up. Correct, right? Now this next movement, 100 Newton meter is coming. What movement it will give you? We have seen in previous classes. This movement is M by L. M is the movement acting wherever it can act. It can act at the center point, here, here. It won't change your reactions. Magnitude of movement is M by L. What is length of the beam? 1 meter. What is movement? 100. So 100 by 1 is the reaction offered at both the ends. Now, but the thing is whether it is upward or downward. Now go slow and think about this. I am not doing this, guys. We have already done this before. So there is a 100 Newton meter load. We'll try to push this point P downwards. Correct, right? This Newton. Forget about this 200. This 100 Newton meter movement will try to push it downward. So what you expect? It should give a reaction upward with a magnitude of M by L. What is M? 100. L is 1. So magnitude of 100 should go up. So at point P, this movement is creating 100 Newton reaction upwards. This 200 Newton, because it is equally distributed, is again given 100 here. So what reaction you expect? This is known as free body diagram. So what reaction you expect here? So reaction at P we expect is 200 going up. 100 because of point load and 100 because of this movement. So you have 200 Newton load here and 100 Newton meter movement here. Fine. Now tell me about this. Because of this 200, it is experiencing 100 Newton going up. But what this movement will do? This movement, when rolls upright, will try to push this beam upward. So this R will try to hold it, and it need to give a reaction in the downward direction with same magnitude. What is the magnitude? M by L, which is 100. So this movement, which is rolling like this, will give a reaction. This roller support will give a reaction of magnitude 100 downward. There is one reaction 100 going up. There is one reaction going down 100. 100 minus 100. What is the reaction here? 0. Please do your calculations. This is your exam numerical. You can happily spend some 2 minutes to solve this numerical. It is asked for 2 marks. And convince yourself that these reactions are proper. If not, revert to the previous lecture in which I have written these equations. I have done equilibrium conditions like forces balance in y direction and movement about any point is 0, and we end up with the same formula. This is a shortcut for you for your GATE exam. Now once you have this, I want you to tell me, they are asking what is the correct bending moment diagram. Tell me guys, I am not doing shear force, this is left to you. We can discuss this in our group or in portal, but tell me what is the bending moment. So what is force here? I am start from right hand side, 0. I will reach here. What force we have on the right hand side? Still 0. What force? 0. What force? 0. So there is no force and movement present from this point to this point. So once I will reach midpoint, right? It is a straight line. There is no movement present. Correct? Now what do you expect? Now we have a doubt what we should do. So I will start from left hand side. Again, what is movement here? 0. Once you come here, force into distance movement, force into distance movement, force into distance movement. What do you expect movement in this zone? It should be constant or linear or parabolic? Constant. Why? No, sorry, linear. Why? Because it's a point load, right? Shear force diagram is constant and bending moment diagram is linear. So we know this is our sign convention, right? So this is positive. So it will take us top and we'll reach here. Now what do you expect at this point? dip. Correct, right? Now why dip? Now the next property and the last property for you people. What is this property? Whenever you have a movement rolling up in your diagram, your bending moment diagram will do up and down. This is the huge property, guys. It looks simple, but okay. And out of these 4 options, your correct option was option A. Alright, so this is the question asked in your exam. The option is A, and what is its magnitude? 100, whatever movement comes here. I hope it is clear to everyone, and this is positive. This is your 2019 AE question. Alright, just for the reference, like you should know how they are asking this in your exam. There will be a separate lecture of all the exam numericals and maybe additional numericals. I hope you know the concepts. So I'm not writing these properties. Maybe you have noted down in the entire lecture. If not, please refer back or open your study material and check these properties so that we can close this lecture. Just summarize the points. Shear force, follow sign convention, which is known as run, right, upward, negative. You can change it towards left hand side accordingly. I hope you know this. Then bending moment diagram, we have seen somewhat these bending moments as positive. Sometimes we name it as sagging. That is smiley face, positive. Alright. Then next is, if your shear force diagram is 0, there is no force, then the corresponding bending moment diagram will be constant and it is referred to as pure bending. And if your shear force is linear, if your shear force is constant, your bending moment is linear. If your shear force is linear, your bending moment is parabolic. Point loads will give you constants and your bending moment diagram will be linear. Then UDL, your shear force is linear, your bending moment diagram is parabolic. Alright. Area under your shear force diagram will give you bending moment. Your slope of bending moment diagram will give you shear force. All these things I have already discussed, I have already written. I'm just summarizing what we have done. Wherever you see a point load, your shear force diagram should find a dip. It should go up and it should come down, it should do something. And we have seen in the last numerical, wherever you find a movement, your bending moment diagram should go up and down. Definitely it should go up and down, guys. It cannot be linear, it cannot be parabolic. At that point, it should suddenly have a jump, it should have a step. Then only your bending moment diagram is correct. So it is an important note for you. When anything like this comes in your exam, right? Look all in the 4 options where you got the dip. The options they have provided, all 4 options were having the dip. So it's better to calculate this. Simply supported beam, you should always calculate reactions. For cantilever beam, it is not required. Now what you will do is go to your portal, go to your study material books. I have given enough solved numericals of shear force bending moment diagram there. Previous year numericals are solved. In portal, in bending test, you will find enough numericals to practice for shear force and bending moment diagram. If you're convincing yourself, then you can happily close this topic and we can move on to the next topic, which is known as, in the coming lecture, we'll be talking about shear flow and shear center calculations. So now you have a rough idea about shear force and bending moment diagram. So we'll talk about this. Any doubt, please let us know. We'll talk in group or post your doubt in doubt clearing session or post it in portal itself and we'll move forward. Alright, so we'll stop here, guys. Thank you.